Let's talk about cumulative distribution function in binomial distribution. Before that, let's talk about binomial distribution. So in binomial distribution model, the number of successes in n independent trials of a binary experiment. That is an experiment in which there are two possible outcomes, either success or failure. The probability mass function of the binomial distribution gives the probability of exactly key successes in n trials. That means if we do n number of trials and case that success event, and the probability of that success event is p, then the probability of getting k number of successes in n trials will be given by this expression. Here nck represents the number of ways to choose k successes from n trials. Now let's talk about cumulative distribution function. CDF of a random variable capital X is a function that gives the probability that will take a value less than or equal to f. For the binomial distribution, the CDF is just the sum of probabilities of obtaining various successes ranging from 0 to x. So here you can see this is and this is almost the same. The only difference we have is this sum term, which is from 0 to x. Now let's talk about the implementation. The first two lines are for loading the Python libraries. The next uh, specifies the parameters. So the first parameter n is the number of trials. Okay, p1 is the probability for the first distribution, p2 is the probability for the second, and p3 is for the third. Okay. And here we are taking a range of values from 0 to 20. The next line is for the CDF of first distribution. This is the CDF for second distribution. This is for the third distribution. And the next following lines are for the plotting. So if we plot it, you can see three lines. Okay. So in first one, you can see that it is increasing very rapidly. That is for 0.05. It is increasing rapidly and reaches to 1 very quickly. So this is happening because the probability of achieving a high number of successes is very low, and the cumulative probability accumulates rapidly for a low value of x. So for a very low value of x, it accumulates quickly. So that's why it reaches quickly to the 1. For the second one is equal to 0.2. We see a more even distribution of cumulative probability with a moderate probability of achieving successes spread across the range. And for the third, p is equal to zero point 0.6. This reflects the higher likelihood of achieving a large number of successes, causing the cumulative probability to spread out more gradually over a large range of Fs. So that's why we see that after a very long accumulation of x values, it reaches the value of 1 for fx.